Alright, so in this video I'm gonna be talking about another approach for event extraction, and this model OneEE has some advantages. It can handle nested events, it can handle overlapping events, and it does it very fast, and it's called OneEE. The model is called OneEE. So I'm going to be focusing on this paper in 2022, which uses this reformer, which is an enhanced transformer with rotary position embedding. Event extraction is an essential task of information extraction, which aims to extract structured event information from unstructured text. Most prior work focuses on extracting flat events while neglecting overlapped or nested ones. A few models for overlapped and nested event extraction includes several successive stages to extract event triggers and arguments which suffer from error propagation. So we design a simple yet effective tagging scheme and model to formulate event extraction as word-word relation recognition. So we call it OneEE, as I said. The relation between trigger or argument words are simultaneously recognized in one stage with parallel grid tagging, thus yielding a very fast event extraction speed. The model is equipped with an adaptive event fusion model to generate event-aware representations and distance-aware predictor to integrate relative distance information for word-word relation recognition, which are empirically demonstrated to be effective mechanisms. So these are examples of three kinds of events, including a flat event. So this one is flat event. This problem is already solved. Maybe 15 years ago. But nested events and overlapping, especially nested events, this is a very serious and very hard problem. Even state of the art are less than 70% or 75%, let's say. And so two examples to illustrate our tagging scheme. We formalize the overlapping and nested event extraction as word-word relation recognition. So for example, here we have investment event. Another event is transfer share. So when we say ST and SA, it means relation between head and tail boundary words of a trigger and argument. So this is argument, this is trigger, and the relation between them. And when we say this RS, RORT, it means the relation between trigger word. So this is the relation between trigger words and argument words, and with the role subject, object, target, and proportion. So this is the architecture. You have adaptive event fusion layer after getting the contextual representation from BERT. Then we do joint prediction layer. So the goal of event extraction includes extracting event triggers, like for example this acquired, which is an trigger. We can formalize overlapping and nested events like this. So given an input sentence, we have n tokens and event types. The task aims to extract the span relations and the role relations between each token pair. So these relations can be explained like this. And S is the span relation, indicating that Xi and Xj are the starting and ending tokens of the extracted trigger span or argument span. So this is called trigger span. This is called argument span. For example, the span is from here till here. Argument span from here till here. Because our reference is always trigger. So the architecture consists of three components. First, the BERT model, as I showed you, then an adaptive event fusion layer, which consists of attention model and true gate, which is used to integrate a target event type into contextual representations. We leverage BERT as the encoder and then max pooling to produce word representations. Since the goal of our framework is to predict a relation between word pairs for the target event type, it is important to generate event-aware representations. Therefore, to fuse the event information and contextual information provided by the encoder, we design an adaptive fusion layer. It consists of an attention model, modeling the interaction among events and obtaining the global event information, and two gate fusion modules for integrating the global and target event information with contextualized word representations. So this is the attention mechanism that we can use. These is query keys and values. So it's just a dot product. And here we have gate fusion mechanism, which we design it to integrate two kinds of features and filter the unnecessary information. The gate vector, as you see G here, it's a gate vector. It is produced by a fully connection layer with a sigmoid function, which can adaptively control the flow of the input. And P and Q are input vectors represented by this equation. And so we leverage the attention mechanism to obtain the global event embeddings for each contextualized word representation. So given a set of randomly initialized event type embeddings, where M is the number of event types, the calculation is like this. And it is the output of the attention mechanism. So to encode the global event information into word representation, we adopt a gate module to fuse the contextual word representation and global event representations. After that, we employ another gate mechanism to integrate the target event type embedding and the output of the last gate module. And the overall process can be formulated like this. And then we have joint prediction layer. For each word pair, we calculate a score to measure the possibility of them for the relation. To integrate relative distance information in word pair representations, we introduce distance-aware score functions. For two vectors, P sub I and P sub J, we combine them with corresponding position embeddings, and then calculate the score by dot product of them. So positions are very important, and R sub I, R sub J are position embeddings of P sub I and P sub J. So we can obtain the span score. This is the span score, and the roll score. This is the roll score. We are scoring the spans and the rolls using these informations. So for the score, where star denotes the relation S or R, our training target is to minimize the variant of circle loss, which extends softmax cross-entropy loss, to figure out multi-label classification. So, in addition, we introduce a threshold score, delta. This is our threshold score, noting that the scores of the pairs with relation are larger than delta and the other pairs are less than it. The loss function can be formulated like this, where this omega star is the pair set of relations and delta is set to 0. So we enumerate all event types in the selected event type and get the total loss. During the inference period, our model is able to extract all events by parallelly injecting their event type embeddings to the adaptive event fusion layer. So this is a decoding case which has 4 steps. So the first step is that we get starting and ending indices of the trigger or argument. Second, we obtain the trigger and argument spans. Third, we match the trigger and argument according to this relation star relations. And the fourth step is that the event types is assigned to event structure. So we repeat these 4 steps for each event type. And the data set, this is an important data set, Genia 2013, which is 2,000 events they use it for training, 2,000, and some for development and testing. You see the F1 score of this model is 73, still less than 75%. So there are still room for improvement. You see, this is trigger identification, trigger classification, argument identification, argument classification. You have precision, recall, and F1 score for all of them, because they compare it with old idea of flat event extraction and different models for if they cover overlapping and nested events, so these are more important. But this model is an improvement. And so you see that for Genia 11 and Genia 13.